Welcome to my crash course on OpenSCAD. OpenSCAD is a really cool program, a great way to design things, in particular designing things for 3D printing. But before you can use it, you need to download it and install it. You can just go to this link, openscad.org/downloads.html. It is free. You don't have to pay anything for it. It is open source. It's just a great piece of software that somebody has made available to us because they love us so much, and we are grateful. Okay, now once you've downloaded and installed OpenSCAD, actually you should probably pause here until you've done that, then come back. So you're back. I now assume you have it installed. You want to run it, and when you run it, you'll get a screen that looks like this. You can click on New to start a new project, open a new file, or you can click on one of, it keeps track of the recent files you've worked on, click on one of those and click Open. You can get help. There's also some example files you can open to learn more about OpenSCAD. I'm going to open it on my computer right now, so I just search for OpenSCAD. There it is. I click on it to start it, and here we go. There's the screen I told you about, and I'm going to click on New. There we go. And here is a new file here. Let me give some space here. All right, and so this is OpenSCAD. Whoops, I lost it. Let's bring it back. There we go. So here's OpenSCAD. And what you see is there's like this 3D view over here that shows you your project. But unlike most CAD programs, rather than coming over here and clicking and dragging and drawing things in our 3D design space, OpenSCAD is actually a program that, like, you describe the three-dimensional object in a text file using its special language, and then it takes that text file and renders the three-dimensional view. So this editor over here, we're just editing a text file. So if I come over here and say File, Save As, and let's put this on the desktop just to make things fast, and I'll call it something. Okay, there we go. And now, this is just basically a text editor here. This is a text file, and I can open it up in any text editor and look at it. And let's put some code in here. So in this text file, we just describe the scene that we want. Like, I want to make a cube, and I'm going to make it, you see it's telling me how I can, different parameters I can give here. Let's make it 10 units wide, 5 units deep, and 7 units high. So I say the shape, then I have open parentheses, and I give the parameters that describe that shape. And for the cube, I can give it one parameter, which is a vector that gives it an x and a y and a z dimension. So in OpenSCAD, vectors are enclosed in square brackets. So then at the end of your shape, you put a semicolon that says, I'm done describing that shape. And if I save this file now, save it, it renders over here. And here's my cube. Okay? So I've made this cube, and you can see it is 10 units long in the x direction. You can see that. Here's 10, 20. So it's 10 units long, it's 5 units deep, and 7 units high. Okay? So there's my cube. I described it. Now, when I push this button here, it updates the 3D view. But if you click on Design and to make sure Automatic Reload and Preview is checked, it'll automatically update that anytime you save the file. So if I come over here and say, no, let's make it 17 tall, when I hit Control S and save the file, it automatically updates. Okay? So this is our text editor where we can add different things. Let's add another cube to this file. Let's make this one 20 units wide, 10 units deep, but only 3 units tall. And I end with a semicolon. When I hit Control S and save that, now I've got the two cubes together. Now I've made a shape. Okay? Now, in the 3D view window, if you left click and then move your mouse, you can change your view. If you right click and move your mouse, you can pan it around. You can move the center. Okay? And then there's some, if you use the scroll button on your mouse, you can zoom out and zoom in. Okay? There's some cool buttons down here. This one updates the view, which we shouldn't need to push if I have Automatic Reload and Preview on. Okay? We'll talk about this button later. This one kind of zooms And, you know, so if my object is off the screen, if I click this, it'll automatically put my object in the center with the right zoom. If I'm like zoomed way out and I click this button, it'll give me a good zoom. Or if I'm zoomed way in, I can click this button and it'll basically center your object in the view with a zoom that makes it all fit. You can use the plus and minus buttons to zoom in and out. If you click this button, it goes back to its default view, okay, which isn't necessarily what you want. There's also some predefined views. Like if you're trying to align things precisely, sometimes it's nice to see the object from the front. If you click this button, you're looking at it right from the front. If you look at the coordinates here, right, we're looking right down the x-axis. This one right here will show it from the back. This one will show it from the top, from the bottom, and this will show us from the left side and the right side, okay? Now, when we look at our object, this button here will give us like a perspective view. See how the things get smaller as they move further away? So it's kind of a more realistic view. But if I click on this button, it gives me, instead of perspective view, it gives me an orthographic view where things don't get smaller as they move away. So the perspective is more realistic, but usually the orthographic is more useful for designing things because, you know, if you want to line things up, you want to sight down something, you don't want things to fade away with perspective. So orthographic view is kind of like seeing something from really, really far away through a telescope such that, you know, the size doesn't really change as we move back, whereas in the perspective mode, it does. So I usually like orthographic. Now, let me make this window a little bit bigger. There's also a button to turn on or off the axes. So you see here, this over here, it tells us X is this way, Y is this way, Z is this way, but then the actual axes are here. And then when you have the axes on, you can decide to either turn on or off the labels that tell you how big things are. So if you want to see how big things are, the labels are really nice. If they're getting in the way or confusing, you can turn them off. You can turn the axes off entirely, whatever you want to do. Okay, so that's your basic interface. And then down here, it just shows basic, the console tells you different things. Like, you know, if I have an error, you know, like if I only gave 2 coordinates, it's going to be like, wait, you're supposed to have 3. Cannot convert size 20,10 parameter to a number or vec3 of numbers. So it's mad because I gave it a vector that only had, you know, length and width, and I didn't have height. So it'll tell you where your error is, and it'll give you different information. Okay, so that's the basic layout of the OpenSCAD development environment. Okay, now I'm going to show you some of the basic shapes. We're going to start with the cylinder, the sphere, and the cube. So how do you make a sphere? So sphere is one of the commands it recognizes. I do open parentheses, and you can see I get this drop-down list telling me things I can put in. If I just give a number and then hit my semicolon, right? The semicolon means I'm done describing my shape. I get a sphere, okay? And if you look at that sphere, if you look at the numbers here, there's 10, there's minus 10. So it's a sphere with a radius of 10, okay? So if you don't tell it whether it's radius or diameter, it's just 10. Or I could come in and I could say R equals 10, and it knows the radius is 10. If I say D equals 10, it knows I'm giving it a diameter instead of a radius. So if I save this, now my sphere is half the size because I told it I wanted to have a sphere with a diameter rather than a radius of 10. So you can tell it whether you're giving this parameter in terms of a radius or a diameter. Okay? All right, now let's do a cylinder. With the cylinder, you've got to give it at least 2 parameters. A height, so I'll say h equals 30, and a radius, let's say r equals 5. Okay? And I do my semicolon, and I save. All right, so you say I made a cylinder that has the same radius as the sphere, so it just fits right on top of my sphere. If I make the radius smaller, now I have a cylinder that's sticking out of my sphere, right? Or I can make the radius bigger. So now, here's my sphere, here's my cylinder. If I just want to see my cylinder, I can delete the sphere, right? Get rid of the sphere. Now I just have my cylinder, okay? Let's bring the sphere back. Another thing you can do, this is a really nice thing to know, is if you put 2 slashes in a row, that tells OpenSCAD that everything starting with those 2 slashes to the end of the line is a comment. It's something to be ignored. So now if I save this, the sphere is gone. So the text is still here, but these two slashes say everything from here on, they don't count. Just ignore them. All right. So if you want to like get rid of some code temporarily to check something out, you can put the two slashes. We refer to that as commenting code out. You can also use the two slashes to add a comment, like this is the main cylinder. Okay. And comments are really good because as you start designing things that are complicated, you'll come back to your designs and you'll be like, what in the heck was I doing? I have no idea. So it's really good to have comments everywhere. Okay, so we did our sphere, we did a cylinder, okay? Now let me show you one more thing you can do. Let me comment back. Let's get rid of the sphere. Let's just look at the cylinder. Here's our cylinder. Notice that the cylinder starts at the origin and goes up in Z, okay? Another thing you can do is you can come along and you can add an optional parameter, which is center. And if you set it to false, nothing will change because false is the default value for, let me make my text window a little bit bigger. False is the default value for center. So if you don't tell it center, it'll be false. But if I set this to true, it will center the object. So instead of going from the origin up, it makes a cylinder such that the origin is at its center. Yeah? Cool, cool. All right, another thing you can do, let's get rid of that for now. We'll just go back. I have a cylinder with a radius of 10. There it is. You can give it 2 radii. Instead of giving it 1, I can say R1 is 10, but R2 equals 15. And what that does is it makes kind of a conical shape where the bottom has a radius of R1 and the top has a radius of R2. I could also change R2 to D2. And there we go. So now the bottom has a radius of 1 and the top has a diameter of 15. Right? If you wanted to make a cone with a point at the top, I can just say R2 equals 0. And now it comes to a point at the top. And I combine that with centering if I want. Yeah? Whatever. So that's a cylinder. So we've done spheres and cylinders. I'm going to show you one more basic shape called a cube. And with a cube, you give it a vector that gives its length and width and depth. So length and width, or width, depth, and height are not like 3 separate parameters. They're like one parameter that is a vector that has 3 things. So vectors in OpenSCAD are values inside of square brackets separated by commas. So I can say, like, let's make a cube that is 20 units wide, 15 units deep, and 8 units tall. And so I put it inside the square brackets, close the parentheses that say I'm done sending parameters to my cube, put a semicolon, and save it, and there's my cube. All right? Notice that the cube starts at the origin, and then it extends out 20 units in X, 15 units in Y, and 8 units in Z. If I want to make it taller in Z, I can make that 18 units in Z. And when I save my file, it automatically updates, and there it is. An optional parameter you can give a cube is center. If I say center equals true, now instead of starting at the origin will be right in the middle. So instead of having the origin at one corner, it makes the cube such that the origin is in the center. Okay, so here's our centered cube. I can make a cylinder to go with that has a height of 30 and a radius of 4, and I save it, and now I can start building complicated things this way. Okay, all right. Another cool thing about the cube is if you wanted something that's really a cube, that the length and the width, depth and the height are all the same, you can just give it one parameter, and it will assume that X, Y, and Z dimensions are all the same. So you can just give it one parameter, and there's your cube. Or, you know, I can do this without centering. And now my cube sticks off to the side. And I can build different objects by putting these different shapes together. And that's the basic idea with OpenSCAD. Okay, so let me tell you about variables and comments. We already talked about comments for a little bit, right? I just said I can be like, you know, this is the main shaft for the rotor, right? And then when I see this, I've got these comments, and I can be like, this is the key to hold the main shaft, right? I can give these things meaning, right? And let's center our cube. All right, there we go. So I've got this code here. So comments are really nice, both for temporarily getting code to not execute, but also so I can label things so they make sense. But this code still has some other problems. It has what are known as magic numbers. H equals 30. What in the heck is 30? Huh? I mean, where did that come from? R equals 4. You come to look at your code a few days after you wrote it, and you're like, oh, why did I write 30? What does 30 even mean? Just having numbers like that, what we call magic numbers, that just magically appear in the code, it's really annoying, okay? So the first thing we need to do is we need to think about what are the units of our numbers. It turns out OpenSCAD does not actually deal with units. They're just numbers, right? But most 3D printing software assumes units of millimeters. And so everything, when I do OpenSCAD, I usually just treat the numbers as millimeters. So I will make a little comment that says, all lengths are given in millimeters. Okay, now I know that. And then I'm going to say, okay, the main shaft has a radius of 4. Where did that come from? Oh, well, I looked this up in the parameters. Let's not just plop that 4 into the cylinder. Let's actually make up a variable. So I can say r main shaft equals 4. Now I can come in here, instead of saying 4, I'm going to say r main shaft. And then whenever in my code I see r main shaft, I'm like, oh, that's the radius of the main shaft. That's where that 4 came from. If I drill a hole in something that fits that shaft, and I'm like, why is that hole like 4.1 millimeters in radius? I can be like, oh, no, I'm going to write r main shaft plus a little gap, right? And so the code makes a lot more sense when you use variables. And let's label our variable. I can do like the radius of the main shaft. So that's even more meaningful than just r main shaft, right? And then I can be like the length of the main shaft. All right? And so I'm going to be like L main shaft equals 30, right? And then I'll come down here, instead of typing 30, I'll type L main shaft. And then everything makes more sense, right? I can be like width of key, and I'll be like W key equals 20. And then I'll come down here and I'll say, whoops, W key. So instead of having magic numbers in my code, I define these variables that store the numbers in meaningful variables with descriptions, okay? Now, when you describe variables, there's a few things you should know. The variable names have to start with a letter. It can be upper or lowercase, all right? You can have numbers in them, I could do that. They can have underscores, but they cannot have spaces in them. And you can't start your variable name with a number or an underscore, all right? So you can make these variable names. And also, when you define your variables, you give the name, you make up the name you're going to use, and then you say equals, and you give it a value, and then you put a semicolon. You have to have a semicolon at the end that says that's the end of this statement, all right? You can also define vectors. So I can be like, let's do this. Width of the key, depth of the key, and I'll say like D key equals 15, height of the key, H key equals 7. And then I can come down here and I can give this thing W key, comma, D key, comma, H key, and make, something that's not perfectly square, right? That has different dimensions. And in fact, if I want, I can come up here and I can say dimensions of key, and I can be like dim key equals, and I can just make a variable that is a vector. D key, H key, if I want to, right? And then I end with a semicolon, and then here, instead of this vector here, I'll just use the variable, dim key. Everything works just fine. Here's a really weird thing about OpenSCAD. If you think of it like a programming languages usually go like, I go straight down, and if I were to take this and put it down here, you'd say, oh, you're going to have trouble with this cube because dim key hasn't been defined yet. Well, save that. OpenSCAD is totally fine with it. If you do variable declarations, even if they're out of order, it'll find them. One thing you don't want to do, though, is to try and change a variable. They aren't really variables. They're more like constants. If you like define a variable to be something and then try and define it again somewhere else, if I save this, it's going to give me an error. And in fact, I'm not going to save it and show you this error because sometimes OpenSCAD will like crash and you have to go to Task Manager to kill it if you do this. So don't define variables twice. It's kind of annoying because sometimes you'd like to go through and change a variable and do something again with a different value. There are ways to do that, but it's not redefining variables, okay? All right, so there you go. There's variables and comments, super important. Okay, now there's a special variable. There's some special variables in OpenSCAD that are like things that are internal to OpenSCAD. They're not variables you make up. And they start with a $sign. And the one I'm going to tell you about right now is $fn. And $fn is a setting that determines, so if we look at our cylinder here, it's not really round. It's kind of like made up of line segments. So OpenSCAD doesn't really do curves. It does line segments. And we can tell it how many line segments we want to use when it makes a circle. And that Fn is exactly that. So if I say Fn equals 6, $f, now it's going to, whenever I make a circle or a sphere or a cylinder, they're going to be 6-sided, all right? So I can make this bigger and make it a better approximation to a real cylinder, right? So the bigger you make it, the smoother it'll be, but it also takes longer to render. So if you make these very big, it can really slow things down, all right? So just beware of that. Also, let's say I make it a big number because I want things smooth, but let's say I actually want this key, this cylinder, to be hexagonal. In the cylinder statement, you can come and you can add the parameter Fn equals 6, and just for that cylinder, it will override the global value for Fn, right? So let's make a sphere, all right, sphere r equals 20. When I save that sphere, the sphere is still smooth because it's using the default value right here, but the shaft, this cylinder, we're overriding the default value of Fn. I can override the default value in my sphere, and I can say Fn equals 8. And now my sphere is has reduced polygon count, right? It's more squared off. All right, so that's Fn. So that's a special variable that is defined in OpenSCAD, and you can override it in your cylinders and spheres by sending it as an argument. Okay? All right. Next, I'm going to show you the cheat sheet. Okay? And what you can do here is if you click on Help, there's lots of information. If you click on Cheat Sheet, it will open up a web browser. I should have loaded this sooner. Here we go. And it will bring up the OpenSCAD cheat sheet. Here it is. Where'd you go? There we go. And the cheat sheet just basically shows you all the different language things in OpenSCAD. And if you look down here on 3D, you can see here are the different 3D shapes we've done. We've done sphere, we've done cube, and there's different ways you can define cubes and cylinders. A polyhedron's kind of cool, and we'll talk about that in just a minute. But there's all these different things. There's different operators. So the cheat sheet is a really great way to kind of look and see, does OpenSCAD do something that I want it to do? And if you're curious, like if we look here, oh, there's functions. It's got mathematical functions, cosine. Do I send the cosine radians or degrees? Well, click on the link, and it will give you more information. Mathematical cosine of function in degrees, right? And they even give you examples of using the thing. So you go to the cheat sheet and you can click on any of these things and it will give you more information. All right? Let's go back up to our 3D shapes. And next we're going to learn about the polyhedron. Okay? So a polyhedron is a shape where you just basically have a bunch of points and you define where those points are, and then you draw faces around those points. So let's say I wanted to make a pyramid with a square base, okay? And I'm going to let the sides of the base be L and the height of the pyramid H, okay? With a polyhedron, it turns out there's other ways to do this in OpenSCAD. With a polyhedron, basically you can make any shape you want as long as you're smart enough and patient enough, right? Because you've got to go through and define all the points and which points make up a face. So to do this example, first I'm going to draw in the hidden lines, right? There's, you know, the things that are in the back. And I'm going to label each of the points on the bottom, A, B, C, and D, and the point at the top, E, okay? And I'm going to define my coordinate system like this, right? So that the origin's in the middle, this is the X direction, this is the Y, this is the Z. So if I wanted to make that polyhedron in OpenSCAD, what I do is I'm just going to come over here. Let's just delete everything and start again. And I'm going to define a variable A, which is the location of point A. And if I look at this, here's the origin. So the X component of A's location is going to be negative 1/2 L. So it's going to be negative L over 2. The Y component of A is going to be negative L over 2. And the Z component of A is just going to be 0. All right, my computer's slowing down. Okay, so the Z component is 0. All right, and point B, it's going to be at L, X component is going to be plus L over 2, the Y component's negative L over 2, and the Z component 0. C, it's going to have a positive X and a positive Y. So C is L over 2, L divided by 2, and 0. Wait a minute. Okay. Now, if I hit save, it's going to be mad because it's like, what the heck is L? Oh, well, I'm going to come up and make a variable L. L equals, how big should we make our pyramid? Let's make it 20 across. And let's let the height be 10. How's that? And I'm going to add some comments. The height of the pyramid. Okay. The length of the square base sides, okay? Points around the base. Okay, so there's C, and then we need D, which is going to be negative L over 2, positive L over 2, 0. And then we've got the apex at the top, which I called point E, and that's going to be 0, 0, H. Okay, so now I've defined variables with each of those points. And with a polyhedron, then, I can come along and I can make any shape I want. So I'm just going to say polyhedron. And if the polyhedron, the first thing you do is you tell it, what are the points? What are the vertices? And I'm going to give it a list or a vector, right, with square brackets. And each element in the list is going to be a vector or list that gives the 3 X, Y, and Z components of the location of that point. So I'm just going to say points are A, B, C, D, and E, okay? And then I close this and I save it, and we don't get anything because we told it what points we're going to use, but we haven't told it to draw any surfaces between those points. So in addition to points, we have to give it faces. And the faces, we give a list of faces, and each of those faces will be a list of points. So for example, to draw this face right here, it's going to be points A, B, and E, okay? So if I do A, comma, B, comma, E, it's mad. It's like, wait a minute, what the heck? It doesn't want us to give it the actual locations of those points. We've already given the locations of the points here. Now it's saying which of these points do we want to use. So I want to use the first point, which, like most programming languages, the first point has an index of 0, and B has an index of 1, 2, 3, 4, and E has an index of 4. So if we do that, it's still mad. Oh, because I didn't close my parentheses. So I say I've got a list of faces, and the first face is 0, 1, 4. And there you see it. There's my face. Okay, it's drawn that one. The next one, this face right here, is just going to be B, C, and E. Or, since B is 0.1, and C is 0.2, and E is 0.4, I put those in. So I've got a list of lists, All right. And when I save that, I get this next face. Okay. And now let's add another one. So let's add 2, 3. It's trying to give me so much help, I can't see what I'm writing here. 2, 3, comma 4. Oh, and then I need to end that. And there we go. We get that one right there. And then I'm going to add this last face right here. It's going to be D, A, and E. So it's going to be 3, 0, because point A is 0, then 4. And now I have all of those 4 sides. Now I need the bottom. The bottom is just A, B, C, and D, or face points 0, 1, 2, and 3. There we go. And now it's got a bottom. Okay? So with polyhedron, you can basically make anything you want just by defining the points and the faces. But it can be tedious. Oftentimes, you're going to want to use like loops and things to calculate these points rather than doing this all by hand. All right, but those are our basic shapes here. And if we look at the cheat sheet here, we've done sphere, cube, cylinder, polyhedron. You can also import 3D things like STL files and such. And we'll talk about extrusion in a minute, okay? And I'll let you learn about, I'm not going to show you everything today. All right, transformations are really important because, you're probably thinking, great, I can make cubes and spheres at the origin, but what if I want stuff other places? Well, let's come along here, delete all of this, and let's say make a sphere with a radius of 10, okay? There's my sphere. Well, what if I don't want the sphere right here? What if I want the sphere somewhere else? Well, you can come up here and you can translate the sphere. And then you give it an X, Y, and Z coordinate. So I'm going to transform it 20 millimeters in X, 0 in Y, 0 in Z. And I hit save, and notice it's moved. Well, let's move it 20 in X, 10 in Y, and 0 in Z, right? So I can move it wherever I want with translate. A few things to note. First of all, don't put a semicolon after that. If I put a semicolon, it says you're going to translate, semicolon means it's the end of the shape, so you're translating nothing. Now we're done. Now let's move on to the next shape. So without the semicolon, it says, what are you translating? You're translating the stuff below it. So transformations happen or applied to the things below them. Okay? I can also rotate. So translate is one. Another is rotate. So let's rotate our sphere. Oh, spheres are boring for rotate. Let's make a cylinder with a height of 15, radius of 10. There we go. So I got a cylinder, all right? Now I can rotate that cylinder. And remember, the transformations act on the things below them. So I put rotate before the cylinder if I want to rotate the cylinder. And then I give it an X, Y, and a component of rotation. What does that mean? Well, a rotation, an X component means you're rotating about the X axis. All right, so if I rotate 90 degrees about the X axis, it does that. And it uses the right-hand rule. So if I take my cylinder and I put my fingers up and my thumb in the X direction, if I rotate my hand 90 degrees palmward, that's the direction it will rotate. So rotate 90 goes this way, rotate minus 90 goes the other way, all right? Looking at that from above, there's minus 90, and there's 90. And there's 0, there's no rotation, okay? I could also rotate about the y-axis. Let's rotate 90 degrees about the y-axis. Or let's rotate, say, 45 degrees about the y-axis, right? There you go. Same, okay? And if I set that to 0, then there's no rotation. I could rotate in Z. Yeah, that's right, rotate 40 degrees in C. For a cylinder, that probably doesn't mean very much, but let's come along here and let's make it, like, rather than a cylinder, let's make it, let's say Fn equals 6, so now it's more of a hexagon. Now you can see as I rotate this, it actually rotates. If I rotate 30, now I get a point at the bottom instead of a flat. Okay? All right, so that's rotate. And if we look at our cheat sheet, there's transformations. We did translate, we did rotate. Scale is another good one. All right, so I can come along and I can say, here's my cylinder. Okay, let's make it a real cylinder again. Let's get rid of that Fn there. Okay, here's my cylinder. I can give it a scale. If I do 1, 1, 1, it's going to multiply all the dimensions by 1 and not change anything. But if I make the y component of the scale 2, now it's twice as big in y. If I make the x component 3, now it's 3 times as big in x, right? So there's all kinds of fun things you can do by scaling things. Now what if we combine transformations? Let's do translate. Let's translate 20 units in the x direction. All right? And I'm going to rotate 90 degrees in z. What's going to happen? Well, before I rotated it, it's sitting over here. But now when I rotate, I'm always rotating about the origin. And since the object's sitting over here, when I rotate, it moves over there. Okay? And now let's scale. All right? So we'll do 2 in x, 1 in y, 1 in z. And now it's stretched. Well, what if I scale by 2 in y? Well, it makes it bigger, but it also moves it further because, once again, it scales relative to the origin. So each point is 2 times further from the origin than it was before I did that. Okay? So you can combine them. If I change the rotate and make it rotate first and then translate, right? It rotates and then it translates. So it does them in reverse order, right? If I scale first, then it scales before it rotates, and then it rotates before it translates. All right? And so it does them, all of you can have multiple things. You can translate it multiple times. You can rotate it multiple times. And it just applies each one of them in reverse order. So first it'll scale it, then it rotates, then it translates, then it rotates, okay? So with this, you can make all kinds of fun shapes. Now, in my PowerPoint slide, I said, as an example, let's make an X with rounded ends, okay? So I'm going to make an X, okay? And I'm going to make that X by making a cylinder. And let's define the length to be 20 units and the radius to be 5 millimeters, okay? And so then it's going to be like height equals L, radius equals R. So I'm not using magic numbers, okay? And let's center it, okay? Okay, so I have the cylinder. If I want to make an X, probably I want the length to be a lot bigger compared to the radius. There we go. So here is my cylinder, okay? If I want to make an X, I want 2 cylinders, but I want them rotated. So I'm going to take this cylinder and I'm going to rotate it about the y-axis by 45 degrees. Okay, so now I have a slanty cylinder. Now I'm going to copy this and paste it, make another one, but this one I'm going to rotate in the opposite direction. Now I have an X. Pretty cool. But I wanted it to have, as I said here, with rounded ends. How can I make rounded ends? Well, I'm going to put a sphere at the end of each one of these, okay? So I'm going to sphere, R equals R, big R is what I call my variable, okay? So now I have a sphere, but I need to translate it and move it over to the end. So I'll be like, translate, and if I do L, comma L, 0, comma L, where'd my sphere go? Oh, it's way over here. Oh, I didn't want to translate it by L. L is too much, right? Because only half of the cylinder, so I go L over 2. Wait, that's still too far, right? Because I don't want to translate it by L and L. I want to just translate by the X component of L over 2 and the Y component of L over 2. Oh, I'm just going to multiply this by cosine of 45 degrees times L. Sine of 45 degrees times L. There we go! And now I have a rounded end, okay? So I just used some trigonometry and said, to find a point which is L over a 2 away from the origin at 45 degrees, right, I have to use sine and cosine. If I didn't want to do that, I could do this. I'm going to show you a sneaky way to avoid doing trigonometry. What I'm going to do is I'm going to first translate by L over 2 in X, okay? And then I'm going to rotate that by 45 degrees along the y-axis. Oh, and that puts it right there. Right? So I moved it out L over 2 and then rotated it to get it there. If I want it to be on the top one, I'll just rotate by minus 45. There we go. And then I'm going to copy and paste that. I'll do plus 45, gives me that. And then if I, let's see, if I do it again, instead of rotating by 45, I'll do like 90 plus 45, gives me that one. And then if I do minus 90, minus 45. It'll give me that one. So now I have an X with rounded ends. It looks kind of clunky. So let's come up here and set FN a little bigger. Okay, there's an X with rounded ends. Okay, and I used rotate and translate to make my X. Okay, I also said, let's use hole to make a cube with rounded edges. So if I look at my cheat sheet, there's another transformation called hole. And hole is really cool. The only downside of hole is that it can be really slow. But the basic idea with hole is that if I make a hole, and I do open parentheses, close parentheses, and then I do curly brackets, everything inside the curly brackets, it's going to lump together, and then it's going to like make a wrapper around it. So if I put a sphere, r equals r, I'm going to make that sphere. There it is. Okay, there's my sphere. And since hole can be kind of slow, I'm going to reduce Fn there. Okay. So now I've got a sphere. And let's translate this sphere. Minus L over 2, minus L over 2, minus L over 2. All right, so now my sphere is down here. Okay. Let's make L smaller. Just, oh, whoops, that was an L. There we go. And zoom in on this. So now I've got a sphere, but it's been translated away from the origin. Now I'm going to make another sphere, but I'm going to transform it in the plus x direction. So now I have two spheres, but because they're inside the curly brackets for the hole, it like makes the two spheres, and then it like shrink wraps them, puts a wrapper around them. Well, let's make another sphere, and let's have this one have the y direction be positive. Ah, cool. So I've got three spheres. It makes a wrapper. Now let's do one with both x and y positive. Cool. So there we go. Now I'm going to take all of these. I'm going to copy the whole thing. I'm going to make 4 more spheres. Only these ones are going to be in the plus z direction. So now I will have 8 spheres, and it wraps around them, and I can make a cube with rounded corners. So hole is really cool, right? Anything I put in here, it makes those shapes, and then it wrapper around them. And then let's put a cylinder in the middle just for kicks, right? And let's let the height be 2 times L, and the radius be R. And look what we've got. It puts the cylinder in the middle, and then it wraps, shrink wrap around it. And you can make all kinds of groovy shapes with a hole. So holes are a lot of fun. Okay. Modules. Modules are great because sometimes you'll make really complicated stuff like, you know, I'm making, let's get rid of the cylinder. Now I've got a rounded cube, right? And maybe I want to make a bunch of these, and I don't want to have to copy and paste or retype things. What you can do is you can come along and you can say module rounded cube. Open parentheses, close parentheses, open curly brackets. I'm going to indent everything here. I just highlight it all and hit tab. It'll indent everything. And then close curly brackets. So everything between these two pairs of curly brackets are now defined to be part of the module rounded cube. And if I hit save, nothing will happen. Because what a module is, it's like a place where you can define a bunch of stuff for use later. And I haven't used it yet. I've just defined it. But if I now type rounded cube, open close parentheses, semicolon, now it'll make my cube. And if I want to make another one, I just type that again. Oh, let's translate it so they're not right on top of each other. 0, 0, 20. Let's make it 40 so they're separated. All right, so now I've made 2 cubes. All right, I can just call my module to make it again. Pretty nifty, huh? So modules are awesome. Now I can define something once and then use it over and over again. I can even, if I want, I'll rotate it 20, 30, 10, just some weird random rotation. All right, and remember, right, don't put semicolons after these because these are transformations that apply to this shape. This semicolon ends the shape. These transformations do not apply to this shape because this shape is done before we get to the transformations. Okay, now it says make a module that makes round edged cubes. We did that, right? I've got this module, rounded cube. Well, you can also do fun stuff. Like if inside these parentheses here, you can define variables. So I can say like L equals 5, and now all the L's in here, they ignore these global L's because I'm saying I'm going to make an L for use, a variable inside this module called L that's its own thing, right? So now L is 5 inside the module, so I can make L equal to 5 instead of 30. But what's cool is because I've made it a module parameter, I can come down here and I can say L equals 10. And I can make a cube any size that I want because I've defined L here to be a parameter rather than, and in fact, I don't need this global L anymore because we're defining it in here, all right? And I can also say, well, I want R to be a parameter too. R equals 5. All right, and notice if I don't give it L or R, it just assumes the defaults here, okay, 5 and 5. But I can come along and I can say, you know, R equals 1 and make a cube of any size with any radius edge that I want, yeah? I can send these parameters, right? I can make this cube have really big corners, and I can make L really big if I want, right? So a module is a way to make a shape, but you can have parameters in your module that you can use to, so that when you call that shape, you can make it a little different each time. So you can define your own shapes that include parameters. Now, if I don't give defaults, it will be mad if I don't define these. So here I say L equals 10, R equals 1. If I don't define L, it's going to be mad. It says, hey, you need to tell me what L is. But if I say L equals 3, then it's okay, because it's got a default for it. Okay? All right. Then it doesn't complain because it's got a value. All right, so hopefully that explains modules for you. Now, loops are really, really useful because oftentimes you're generating things that you don't want to create every element by hand, right? So for if you want, imagine, if you will, I want to make a bunch of spheres. R equals 2, let's say. Where's my sphere? There we go. Let's say I wanted to make a bunch of spheres. Okay. But let's say I want them like in a ring, right? And so I can be like, well, let's translate the sphere by 30 units in X, right? So there's my sphere translated. But let's say I wanted like a whole ring of them. Well, what I can do is I can come along and I can say, well, let's make that one. Let's copy and paste that. Let's make another one, but let's rotate by 20 degrees in Z, okay? And then let's copy that again, and let's rotate this one by twice as much. And then let's do it again, and let's rotate this one by 60, right? And I can make this ring by copying and pasting, but it's a real pain in the butt, okay? So instead, I'm going to do a loop, and here's how a loop does. A for loop works. You say for, and then you make up some variable. Let's say I is going to be my variable. I equals 0 to 10. And then I do an open curly bracket and a closed curly bracket. And when I save this, what it does is it goes through and it runs the stuff inside the curly brackets with I being equal to 0, then with I being equal to 1, then 2, then 3, then 4, all the way up to 10. So what I can do is I can get rid of all this stuff, and I'm going to put this in my loop. Okay. All right. And then indent that so it looks nice. Indenting doesn't affect how it runs, but it makes it look nice. And so I'm going to rotate 0, 0, 20, okay? But what I'm going to do is I'm going to put I in here. So each time through the loop, it's going to rotate by a different amount. So the first time through the loop, I will be equal to 0, and it won't rotate it at all. Next time, I will be equal to 1, and it'll rotate by 20 degrees. Next time, I will be equal to 2, and it'll rotate by 40, and so forth. And if I make I, since I'm going by 20, I can there we go. 16, 17 gets us all the way around. and 18 is not necessary, okay? Because 20 times 17 is, well, 20 times 18 is 360 degrees, okay? So there it is. I've made a ring, and I don't have to define each of these spheres individually because I used a for loop. So if you say I equals, open bracket, a number, colon, another number, it will go sequentially from one to the other in steps of one. If I go from 10 to 17, I only get these ones. If I go from 5 to 10, I only get those ones, all right? But we wanted to go from 0 to 17 to get all of them. If you add another semicolon, you can do step sizes. So if I do 0, colon 2, colon 17, it'll go from 0 to 17, but in steps of 2. So we'll miss every other one. If I put 1 there, that's the same as having nothing there. Okay, so if you have two colons, the one in the middle is the step size. Okay? Another thing we could do is I could say, well, look, let's just rotate by I, and let's have I go from 0 to 360. And then I can just say, well, let's do in steps of 20 degrees, 30 degrees, 50 degrees, 60 degrees, right? So you can do loops that way as well. You can say, oh, I'm going to go from 0 to 360, but in steps of 60. You can also, instead of using colons to do sequential things, you can make lists, 0, 20, 40, 60. And it will do each one of those 180. And it will just do each one. So if you have a bunch of values separated by commas, it'll go through and do those specific values rather than counting from one value to the next. All right? So that's how a for loop works. So now it says, let's make a rounded ebb cube module using loops. Okay? So here we go. Module, rounded cube. And what parameters do we want? We'll say the length of a side, and we'll default that to 10, and a radius of curvature, we'll default that to 2. Okay, then I do curly brackets. Inside the curly brackets is my module. So I'm going to make a sphere of radius big R. Okay, and then when I call this, I get a sphere, right? But if I wanted to make a rounded cube, what I want to do is I want to take this sphere, and I want to translate it by negative L over 2, negative L over 2, negative L over 2, right? Okay, but then I need to copy this, and I have to go and make all the other corners as well, right? But I don't want to do it by hand, so what I'm going to do is I'm going to do a loop. I'm going to say for ix equals -1, comma 1, do open curly bracket, okay? And then over here, instead of minus L over 2, I'm going to do ix times L over 2. And so now I get one at negative L over 2 for my x value and one at positive L over 2 for my x value, because ix takes on values -1 and 1. Now I'm going to do a nested for loop, iy equals -1, comma 1. All right. And come and indent these, and I'm going to say for my y coordinate, it's going to be iy times L over 2, and then I close my curly brackets. Now I get ones in 4 different places, but I want to do each of those at 2 different z values as well. So let's come in here and nest in another for loop. For iz equals -1, 1. Indent this again. All right, it's wrapping around because my text window isn't very big. There we go. And when I save this, oh, and then I need to actually come over here and change this to iz times that. All right, so I made up 3 loop variables, ix, iy, iz. I said, I want you to take on the value of -1 and then 1. And then each time through the ix loop, it'll run the iy loop. Then one time through, iy will be -1. Next time through, iy will be 1. And then for each time through this loop, it'll go through our z loop. And each time through the z loop, the first time it'll be iz will be -1. The second time it's +1, right? And ix, iy, and iz are just names I made up to use here. And now it gives us all 4 of these corners. And so now I just need to shrink wrap around it by putting all of this inside of the whole transformation. And there's my rounded cube, okay? And let's make FN a little bigger so it looks a little nicer. And as I mentioned, holes can get kind of slow. when you have lots of, you break your circles up into lots of segments, but there it is. Okay, now of course this cube is going to be a little bit bigger than the L I gave it. It's going to be bigger than 10 millimeters. As you can see, it goes out a little past 5 millimeters because we centered our spheres at these locations, right? And then the spheres grow out in both directions. So if I want my cube to actually be 10 millimeters thick, I have to come over here and subtract off 1 radius off of each of these. So I put in parentheses, instead of L over 2, I'm going to move by L over 2 minus R. And now I have a nice module which will actually make a cube whose dimensions are L. Yeah? So there we go. So I have now made a round edge cube module that uses loops, so I don't have to, make 8 different sphere statements. All right? Okay, now let's talk about some of the two-dimensional shapes that are available in OpenSCAD. So if we look at the cheat sheet, there's a list of two-dimensional shapes. Two-dimensional shapes are useless for 3D printing, but you can use these two-dimensional shapes to make three-dimensional things. All right, and I'm going to show you how to do that here. So let's get rid of this now. And let's say, remember our pyramid that we made? Let's make our pyramid, but let's do it an easier way now. So let's let the height of our pyramid be 20, length of the side is 10 or whatever. Instead of making a polyhedron and defining all the points and doing all that effort, what I'm going to do is I'm going to make a square. And its size is going to be L. Okay? And there's a square. Okay? Now notice it's 1 millimeter thick. Well, it's not really 1 millimeter thick because square is a two-dimensional shape. It has no Z, but OpenSCAD shows it to us as 1 millimeter thick so we can see it. But if I go and try and save a file to 3D print, there's going to be nothing here. Okay? I can also give it, instead of just L, I can give it a vector with 2 components so I can separate, designate the width and the depth separately. Okay. But let's go ahead, let's make it actually square. So we'll just say you're L. And let's center it. So now I've got this square and it's centered. And what I want to do is I want to make this not a two-dimensional object, I want to make it a three-dimensional object. So I'm going to use the linear extrude function. And the linear extrude function takes at least one parameter, which is height. And what it's going to do is it's going to, let's say this is 10. Let's call it H, right? No magic numbers. What it does, oh, it didn't do anything because I put a semicolon here, so it's linearly extruding nothing. I get rid of that, it'll linearly extrude my square. And so what linear extrude does is it takes your two-dimensional shape and it stretches it by the distance height in the Z direction. So now I have a square cross-section which has been stretched up a height H. Okay? So you can do all kinds of fun things. You make a two-dimensional object and then stretch it. But linear extrude also has an optional parameter called scale. And if it's set scale equal to 1, nothing changes. So what scale does is it says, I'm going to go from the bottom to the top. By the time I get to the top, it's going to be a factor of scale bigger. So if I said 2, it gets bigger at the top. If I say 0.5, it's smaller at the top. So if I want to make a pyramid, I just say scale 0. So it goes from my square at the bottom, it linearly extrudes it, but by the time we get to the top, it has shrunk down to a scale of 0. So there's another way to make a pyramid. That was a lot easier, all right? And so you can do all kinds of fun things with your two-dimensional shapes. And if I look here, I can make circles, I can make squares. Polygons are like polyhedrons, only you don't need to determine faces, you just do a shape. Like I could do like a polygon. And I could do like, I give it my points. My points are 0, 10, 10, 10, and 0, 0. All right? And that will make a polygon if I get rid of my extrude here. It just takes those points and draws a shape. I start at x equals 0, y equals 10. I go to 10, 10. I go back to 0, 0. And it just draws that shape. I can add another point here. Let's go like down to 5, minus 5. Right? And it just draws the shape. It draws my polygon. And then I extrude that shape. If I wanted it to just be, you know, straight up and down, I can leave out scale or set it to 1. If I want to make it come to a point, I set it to 0, or I can set the scale to 0.5 or whatever. And you can make all kinds of fun shapes that way. Another fun two-dimensional shape is text. And we're going to use text to show you how you could make like a name plaque easily. So what I'm going to do is I'm going to come along and I'm going to make a two-dimensional object called text. And in text, first you give it the string. So my string is going to be my name. Okay? And if I do that, it makes my name. Pretty cool, huh? That's my name. But it looks like it's got some depth. But remember, text is a two-dimensional object. So if I actually wanted to print something out, I have to give it a thickness. So I'm going to use, again, linear extrude. And let's make it, I don't know, 4 millimeters thick. There we go. So now there's my name, 4 millimeters thick. Now you can change how the text is aligned. Oh, before that, you can change the size. I can make it bigger, right? So if I say 20, now the biggest characters are, get rid of the help here, are 20 millimeters tall, right? So if I made it 30, now the biggest characters are 30 millimeters tall. Make it 40, right? 10, whatever size you want, okay? So now the height of the capital letters is 10 millimeters or 1 centimeter, okay? So that size. You can also change the alignment. So there's no center function like with some other things. It handles the kind of the vertical and horizontal centering differently. So I can say H align left. And that says align it so that the left side is at the origin. If I say right, then the text ends at the origin. And if I say center, it centers it. And then there's a vertical alignment parameter, V align. And again, it can be top. Now the top is aligned with the origin. Bottom. Now the bottom's aligned. Or it can be center. Like that. Another option for V-align is baseline. And what that does, let me throw, my middle initial is not J, but I'm going to put a lowercase j in there anyway. And what you can see is descenders. And let's come over here and turn off scale markers because they get in the way. All right, but when you look at this, when I do baseline, the J extends below the baseline. Whereas if I said bottom, it would make the lowest part of the text hit the origin. So that's the difference between bottom and baseline. But let's center it. Let's get rid of the J because that's not my middle initial. Okay, now if I go to 3D print this, each of these letters is going to be printed separate. That's not going to make a name tag, so a name plaque. So let's make a cube below it. And let's make it, well, let's see, let's turn these numbers back on so I can get an idea. Kind of, if I go from like minus 90 to 90, so that would mean like a width of 180 and the 30, and let's let Z be 3 millimeters. All right, and I center that. Oh, center equals true. I'm setting the center parameter true. There we go. All right. Now, yeah, there we go. So there's a cube that's centered, and there are letters that come out of that. And let's make the base 5 units thick. How's that? There we go. And you see, I can also, when I do linear extrude, I can turn on centering. So then it extrudes it and then centers it. But when I do that, my text gets lost, right? Because my cube covers it, right? So if I do center extrude, then it moves the text down. So let's not center. Let's make the text start at Z equals 0. Let's make our cube. And I centered it, but I don't want it centered in X and Y. I want the top of my cube to be at Z equals 0. So what I'm going to do, I'm going to come and translate my cube and move it down by half of its thickness. There we go. So now the top of my cube, and if I do like a front view, you can see the top of my cube is at the origin and the bottom of the letters are at the origin. Okay, so there you go. Two-dimensional objects linearly extruded. Okay, now, one other really important thing that you need to know about are these things called Boolean operations. The main ones are union, difference, and intersection. Let me show you how they work. So if I say sphere r equals 10, okay, there's a sphere, okay? And now I'm going to say cube 2. It needs to be bigger than that, 20. So I've got a sphere and a cube, right? And let's say they're, I've made some object. Now I want to translate both of them. Let's say I want to translate them together by 30 units, 30 millimeters in the x direction. When I do that, only the sphere gets translated, right? Because the semicolon ends the sphere. If I get rid of the semicolon, then I get an error because sphere cannot modify cube. It's its own thing. So what can I do to make them translate together? Well, what you do is you make a union. And I'm going to union them together to make one object. Indent these. So you say union, open parentheses, close parentheses, open curly bracket, close curly bracket. And then everything within the curly brackets are like lumped together, so they're like one object. So now if I translate them, they translate together, right? And if I rotate them, they rotate together, all right? And I can add more things here. So now I've added a cylinder, and now notice, I can do translations inside the union. So let's get rid of this right here. So I've got the 3 of them. I'm going to take the cylinder, and I'm going to translate it 20 in Y. Okay, so now I've got this object. Now, when I do rotate on this, it rotates the whole thing. They've been unioned together, so they're like all of these together describes one object, and then I can rotate it. So that's what union is good for, putting things together. Now I'm going to show you difference, okay? So difference takes the difference of two things. So I'm going to say, let's take a cube. All right. And let's center it. And there's my cube, okay? But it's inside this difference statement, which means if I add anything else, instead of adding it to the scene, it'll actually subtract it from this cube. So if I do a cylinder, h equals 100, r equals 20, center equals true. Now, instead of adding a cylinder, it subtracts a cylinder. It pokes it out, okay? And if I added another, cylinder, let's actually do another one, but let's rotate it about the x-axis by 90 degrees. Boom. All right? And so I can go, and everything I add after that first item will get subtracted from that first item. Okay? So that's what difference does. It allows you to carve things away. And then the third Boolean operation I wanted you to know about is intersection. And what intersection does is, remember the open close parentheses before the curly brackets, you give it a bunch of things. All right, there's a sphere. And as you add things, it will only give you the pieces that are contained in all of them. So if I say now a cube of size 10, we just get a cube of size 10, okay? Let's center it. All right, because this cube is inside the sphere, so inside this cube, that's the intersection of both things. If I make my cube bigger, oh, notice now, if I didn't have the intersection here, let's comment this out. I have a cube and a sphere, but if I intersect them, I only get the place where both of them are, if that makes sense. And if I come along, I'm going to make another cube, which has an x dimension of 100, a y dimension of 100, but z of only 3. So it's true. Then we can pull a little slice out of that thing, right? And if I change the intersection to union, we've got all of these three pieces put together, but when I make an intersection of them, I only get where all of them are, if that makes sense. Okay, so intersection can be really useful as well. All right, so there are basic Boolean operations, union, difference, and intersection. Now we're going to use what we've learned to make a guitar potentiometer knob. So this is the knob that goes on the volume and the tone controls on your guitar. And we're going to make one that looks like this right here. Okay, and here I've given the dimensions. So let's try it and make that. So it's basically, to make this, I'm going to have a cylinder, a cone, and then another cone on top of each other, except I'm going to have some ripples on the edge to make it easier to grab. And then I'm going to drill a cylinder out of the middle so it can slip over and fit onto the potentiometer. And I've got different dimensions here. So to make this tone knob, I'm first going to write down my dimensions. Okay, so I'm going to say the base has a radius of 26 millimeters, or a diameter of 26 millimeters. So I'll say d base equals 26 millimeters. And I save that. Nothing renders because I haven't actually made any shapes. All right, now this bit right here, that radius right there is 19 millimeters. So I'll say like d mid equals 19 millimeters. And then the top of it has a diameter of 17 millimeters. So we'll say d top equals 17 millimeters, right? I'm defining these variables so we don't have magic numbers, so everything makes sense. Now this little bottom section, it has a height of 1.5 millimeters. So I'm going to say h bottom equals 1.5. And then we've got kind of this tapered region right here that has a height of 1.5 millimeters. So I'll say h mid equals 1.5 millimeters. And then the top part is 7 millimeters. So we'll say h top equals 7. Okay? And then the radius of the hole is 6 millimeters. So we'll say, or sorry, the diameter of the hole. So d hole equals 6. Okay, now I've got all of my parameters. Let's start building this thing. So the bottom here is just a straight cylinder. So I'm going to be I'm going to call it, say, cylinder. R equals R. D equals d base because I have diameters, not radius, and h equals h bottom. And notice I can define the diameter and the height in whatever order I want. I did not have to do them, height then diameter. I just say d equals h equals, so it knows which one is which. Okay, and then after that, I have to do this tapering section that goes from 26 millimeters to 19 millimeters. So I'm going to make another cylinder. And I'm going to give it two diameters. D1 is equal to D base, D2 equals D mid, and H equals H mid. Okay? And I do that, and it's mad at me. Why is it mad at me? Unknown variable D min. Oh, D mid. There we go. And you can't see it because it's covered by the other cylinder, right? I need to translate it. I'm going to translate it by H bottom so that it stops at the top of the bottom piece. There we go. So there's our tapered piece right there. And now I need to add this top piece, which again is going to be a cone. So come along here, make a cylinder. D1 is equal to D mid, and D2 is going to equal to D top, and the height is equal to H top. So now we get this cylinder. Once again, though, it's making this cylinder starting at the origin, so I need to move it up so it's on top of the other stuff. So I'm going to translate it by H bottom plus H mid. There we go. And there it is. Okay. So the next thing I need to do is I need to drill the hole out of the bottom. So I'm going to come along and I'm going to say difference. All right. And then I'm going to come and I'm going to say cylinder, D equals D hole, H equals, how high do we want it to go? Well, let's go H bottom plus H mid plus H top. Let's go all the way through minus, say, 2 millimeters. There we go. And, what happened to all the other stuff? Oh, remember, difference takes the first thing and then subtracts everything else. I didn't want it to subtract all of this stuff from my first cylinder. I wanted all of this stuff and then a hole through it. So I'm going to put this in a union. So I'm going to union all of these together and then drill a hole through it. All right, so these are all union together. This is one thing. So this is the first object of my difference. And then I'm going to drill a hole, and what the heck? There's sort of a hole there. But, oh, it turns out OpenSCAD has problems when you cut right to the edge of something. It's like, is that last micron part of the hole or part of the object? So what I'm going to do is I'm going to actually move this down 1 millimeter. So I'm cutting starting from 1 millimeter below, so it definitely gets that hole. But since I'm moving it down 1 millimeter, I'm going to make it 1 millimeter taller. Yeah? And there it is. Now, the thing we don't have are the nice ripples on the edges. Also, it looks kind of clunky. Let's increase FN to 20, let's say. 50. Okay, that looks smoother. Okay. Now, I want the ripples on the edge so it's easier to grip. How can I do that? Well, what I'm going to do is I'm going to come along and I'm going to get rid of the cylinder here and I'm going to make something else. Okay, so instead of that, what I'm going to do, let's comment all of this away so I can work just on that piece. Oh, by the way, so / comments align. If you do /*, it comments out everything until you get to */. So you can comment out multiple lines like that. I should have mentioned that earlier. Okay, so let's just work on this piece. So what I'm going to do is I am going to make a polygon. Right? We talked about polygon. Points equals, what are the points going to equal? What I'm going to do is I'm going to do a for loop inside my points. For I equals 0, steps of 1, 360. Okay? And then I'm going to define my points. All right? And I want my points to come out to a diameter of d mid divided by 2 to get the radius. Okay, I'm going to do some trigonometry. Times cosine of I, sine of I. Okay, and remember, polygon is a two-dimensional object, so I only give it two dimensions. All right, and when I do that, I get a circle because it goes through and it makes a bunch of points. Let's do steps of 20, so that's more obvious. How about 60? Right, so it goes, it makes this point, this point, this point. So it's going, and I'm making an angle. I is a bunch of different angles that go from 0 to 360 degrees in steps of 60 degrees. And at each point, I'm calculating the cosine and the sine of I. I'm making a vector, which is cosine of I, comma, sine of I. And then I multiply by the radius, how far out I want those points to be, which is d mid over 2. Okay? So I'm basically making a circle just like I did before. All right? Now, to make a circle into a three-dimensional object, I'm going to use linear extrude. Height equals h top. Okay, and now I've got a cylinder, but I want the cylinder to taper in so it goes from the d mid to d top. So I'm going to do scale. How much do I want the scale to change by? Well, I want it to multiply by d top divided by d mid, right? So that it starts at d mid and at the top it'll be d top. And there's a cone, just like we had before. All right? So I can put that cone in here instead of the cylinder. All right, so get rid of these comments. Okay, so I'm going to get rid of the cylinder, and instead I'm going to have this polygon that I linearly extrude. Whoops. I deleted the wrong thing. Should be there, right? That was my hole. Okay, so instead of a tapered cylinder, I'm going to have a polygon that I linearly extrude to make that, okay? So now I'm back to where I was before. I'm using a polygon that I've linearly extruded rather than the cone. How does that help me? Well, what I'm going to do is I'm going to come along and I'm going to change the radius depending on the angle. So I'm going to say d mid plus cosine of 50 times I. And now you see the radius changes. OpenSCAD's having some trouble doing this, but it's moving back and forth by 1 millimeter, okay? And it's, as I go around from 0 to 360, it's doing like 50 times in and out. Well, I don't want the notches to be that deep, so let's say 0.2 times that. Now they're smaller notches, all right? And now I want the notches to only go in, right? Cosine goes both positive and negative, so I'm going to subtract off 0.2. So then when it goes out and in, the biggest this extra piece I've added will be a 0, and the smallest will be negative 0.4. And so there we go. There's my rippled thingy. All right. Let's do smaller steps to make it look a little smoother. Whoops. And yeah, there you go. And so I've made a knob. And I made the ridges by making a polygon. If I get rid of the linear extrude, you see it's just a polygon that has the shape that I want, and then I do a linear extrude to make the tapered cone. Okay, so there you go. There's an example of using Boolean operations. I used a union so that when I did my difference, it drilled through everything. And I also used my polygon and a linear extrude to make the ripples. Now here are some common mistakes that people make when they use OpenSCAD. First of all, remember you have to have semicolons after your objects. If you make a sphere, or I've defined, round end cylinder to be a module, when I call that, I need a semicolon at the end saying, that is the end of my object. But you don't want semicolons after the translations or rotations or the scales. Those transformations, if you put a semicolon after them, it says that's the end of the shape and you're translating nothing. All right, so I don't want a semicolon here because I do want to translate the sphere, not nothing, but I need a semicolon after the sphere. I don't want a semicolon right there. So common mistake is misplacing or missing semicolons, so look for that. Here's just a few examples of things that I made. I wanted to make a channeled bolt to go into a little desktop CNC. So these channels, and you have to have a little thing here with you can stick a bolt into and it sticks up. So basically I just made a cube and I wanted to poke a hole for it for the bolt to go through. So I made a cylinder and cut that out. And then I wanted to make a hexagonal shape for the head of the bolt to fit in. So I made a cylinder, but I overrode FN so that it only has 6 sides to make a hexagonal thing, whoops, for the bolt, right? So you can see that I define all my parameters. I make a cube, cut out a cylinder, and cut out a hexagonal shape, which is a cylinder but approximated with only 6 sides. And then I said, oh, it would be nice if the edges of these were rounded so it wasn't so nasty. So what I did is I came in, this is the same code, only instead of a cube, I replaced the cube with a hole that has 4 cylinders. So I made a cylinder at each corner, and then I wrapped it in hole. So now I get something that looks like a cube, but it's got rounded corners. It's 4 cylinders with shrink wrap. And then I said, that's really annoying to have 4 different cylinders. Why don't I just have 1 cylinder and do 2 for loops? Yeah? And then I make a cylinder, I translate it to here, to here, to here, and to here through my loop. So there's an example of something simple that I've made using OpenSCAD. I also made a base to hold a circuit board. So there are these electro-cookie circuit boards you can get, and they have places where you can solder stuff down, and they have holes where you can mount. And I wanted to make a base I could bolt it to. Well, when doing something like that, I think it's a good idea to actually make a mock-up of the actual thing in OpenSCAD so you can see how it fits together. So here at the beginning of my code, I set what FN needs to be. I entered the width, the length, and the thickness of my circuit board. H is how far the PCB should be mounted above the bottom, how much space there is below the circuit board. And then, as you note, the circuit board has 3 big holes and 4 smaller holes. And so The X position of each of those holes, I give that. That's how far each of these holes is from the center. And the diameter of the big holes is 3 millimeters for an M3 screw. And then these smaller holes have an X and a Y offset, which I've put into my code here. And there's the diameter of it. And so then I make a module, which is the actual circuit board I'm trying to mount, just so I can make my mount and see that everything's going to fit okay. So here I basically have a difference. I make a cube, which says the length, width, and thickness of my circuit board. And I translate the X and the Y dimensions to center X and Y, but Z's still at the bottom. And then I go through and I punch these holes, right? So the big holes, they're at plus X hole, 0, and minus X hole. So I let I equal minus 1, 0, and 1, and I go through, and each time through the loop, I make the cylinder and I translate it in X. I translate it by minus 1. Remember, I like to not cut starting at the surface, but a little below so that it for sure, makes that cut. And then the height of these cylinders I'm cutting out is the thickness of the board plus 2, so that when I adjust it down, the hole goes from 1 millimeter below to 1 millimeter above to make sure it really gets cut out. And then I do my small holes. They have to be translated into both X and Y, so I do a double loop. And there's my circuit board. And now that I've got my circuit board, I can go and make the holder for it. So I'm going to start off by making a base here, and it's just a cube, okay? All right? And I make it the length of the circuit board plus some extra stuff, because there's going to be a wall that comes up to hold the circuit board. So I want it bigger by the 2 times the thickness of the wall, because there will be a wall on either side. Plus I want to have a little tiny gap, little space, to make sure the circuit board fits in. So I add a little gap. And the width, I'm going to make the width of the circuit board plus 2 wall thicknesses plus 2 gaps as well, right? And then the thickness of it I'm calling T-wall. So T-wall is how thick each of my walls are going to be. So there's the base. And now I can come and add the sides. So the front sides are cubes that are thickness T-wall, right? And I make both of those. And then I want a ledge to hold the printed circuit board, so I have another cube on either side that's a little shorter that the circuit board can sit on top of. And I've got sides to bookend the circuit board, and I do a little loop to make a wall and translate it, right? So I make a cube, I translate it to the side, and then I say, well, let's scale it. So when I is equal to minus 1, it'll scale the X dimension and flip it over here. When it's equal to plus 1, it just scales it by 1 and doesn't move it. All right, and then I'm like, okay, now I need to add places for the screws to hold the circuit board down. So to add mounts for the big screws, what I'm going to do is I'm going to make little cylinders here, and I'm going to make them a little bit bigger than the holes I want, okay? And then I'm going to punch a hole through the cylinder, which is a little bit smaller than the hole I want. Why a little bit smaller? Well, these screws need to make a thread, right? So I could put threads in there, but what I've found is for small screws, just making a hole that's a little bit smaller than the diameter of the screw, since it's plastic, when I put the metal screw in, it'll just cut threads for it. So for like an M3 or an M2 screw, I'll just make the hole just a little bit smaller than the diameter of the screw, and it will cut in as I, thread as I drive the screw through. Incidentally, what I've found in 3D printing with 2 different brands of 3D printers is external dimensions seem to be pretty accurate. Internal dimensions, like holes, are often just a little bit smaller than you expected them to be. So if you really need a clearance hole for something, make it a little bit bigger to make sure you have space for something to go through. And then I do the same thing for the small screws again, right? I'm going through an X and a Y scaling double loop. And again, I have a cylinder, which is the diameter of the screw plus a little bit, and then I punch a hole, which is just a little bit smaller than the size of the screw that I can cut into. And then I uncomment the printed circuit board thing to make sure everything fits, and I look from above and make sure the holes in my circuit board line up with my mount points and everything. Once I'm happy everything's good, I comment out the circuit board, and I render this thing right here and 3D print it, okay? Here's an example of a window clamp. We're changing some curtains in my daughter's room, and we had to remove the window, and it had these plastic clamps that held it in, but they were old and they disintegrated. They broke. And so I went through and measured the different dimensions of the old window clamps, and then I made a polygon with these different points, and then I linearly extruded it, and then needed to be a hole for a screw. I measured where that was supposed to be, and I used a difference to punch it out, and then I printed these out, and we were able to clamp the window back in. All right, so now we've talked about designing things. This button here, if I go back to my thing here, this button is the preview, right? Which, since I have automatic reload and preview, I don't have to ever click that button, because every time I save the file, it reloads and does the preview for me. But this is just a preview. If you want to actually make a fine rendering that you can 3D print, you push that button right there. And when I push that, notice it's taking some time. You can see kind of progress happening here. And depending on the print, how complicated it is, it can take hours to do this rendering. This one, it looks like it's going to finish in a few minutes, but we won't wait for that. So you either push that button, go to Design, Render, or just press F6, and it will do that rendering. And then once this rendering is done, right, the green progress bar will fill and then disappear, and it will say in the messages here, finished rendering. Once that's done, you hit F7 or click on File, Export as STL, and you can export. That beep just means that my file finished rendering. See, now it looks much nicer. So now I've done that, I can export it. So I come up to File, Export as STL, or you can just click F7, and it will bring up a file dialog, and you can say, let's save this as something.stl. And now it's saved, STL export finished. Now I have an STL file I can pull into my 3D printer slicing software to print something up. So once you've got your design done, you click on this or click F6, and then you wait until it says rendering finished. Then when it's done, you either hit F7 or File, Export as STL, and you can save an STL file, which is what you use for 3D printing. Okay, so now let me know if you have any questions. If you're in the UVU community, in the UVU physics department community, I'm glad to help you. I have some libraries that might be helpful for you if you need to actually cut threads and things. I also have a library with kind of standard bolt and nut and washer dimensions for different types of bolts and screws. And I use those like when I'm putting things together to make sure that bolt heads are going to clear things and things. So I'll throw them in and put them in my designs temporarily to make sure everything lines up. I also have other miscellaneous things like representations of several servo motors and bearings and things. So if you need help with something, let me know. I might have something already written that can help you. I can give you advice. Here's just some examples of using threads, of libraries. So here I've included some different libraries I've written to make things easier. This is a file where I'm defining some optics mounts that I'm going to print out for Physics 4210. This is like a kinematic mount showing both the top and the bottom. And you can see here this part is threaded. I have a library that I wrote to make threads that can do that much easier than trying to do it by yourself every time. Also, if you're curious, I can show you how to write STL files not using OpenSCAD, but actually coding them directly in Python. It's a little more work because you have to actually write the STL file format. But it turned out for me this was really nice because I was able to write a file where I could make mounts for different lenses, right? If I buy a lens from Thor Labs, it's nice but expensive. If I buy one from Surplus Shed, it's cheaper, but it'll be some weird diameter that I can't get a standard mount for. So I wrote some Python code where I can put in the parameters of the lens, and it will actually spit out an STL file for a lens mount for me. So yeah, I have loads of other information I could give you if you're interested, but let me know. That's the end of our crash course.